right, everyone, we are on our third problem, and we're looking at stability, controls, control effort, and lots of good and fun things here. So I'm going to just define my values here. I don't even think I'm going to need to actually. Definitely won't need to look at it here. Whoops. So let's go ahead and we'll move through here. I'm just getting my Mathematica set up. So we are going to be setting up following problem. We're going to go down here. All right. So here's our handy table. So we're told our R of t is 10. Our P of S is equal to, let's go ahead and set this up. So S plus 1, S plus 1, S plus 5. Our C of S is equal to K1 times S plus K2. So actually, this is a PD controller. So we have our G of S, we have our R of S. We can actually very efficiently, let's go ahead, we'll define, actually I'm going to define it up here. So I'm going to define, so where there's no noise, there's no disturbance, so my C effort is equal to, I'm going to define this up here, which is U over R, so C S divided by 1 plus CS times PS. So that's our control effort, U over R, our air, our tracking air, control effort, steady state air, so tracking air equals, so E over R, which is 1 over that. Excellent. We'll do full simplify. So that's that. So we can now state, so I'm going to actually just define it right now as well. So my Y of t is going to be equal to my inverse Laplace transform of my GS times my RS, S, and T. So it looks nasty. And then we'll do, I'm just going to call it CT. CT. So that's my CT is going to be my C effort times RS, and my ET is going to be tracking air times my RS. Excellent. So we've got those values. So now let's figure out stability. So I'm going to expand this. So let's look at our system here, and we can see that we have the following values. So we have 1, then it's K1 plus 6, and then it's K2 plus 5. So that's our system. It's actually only second order in this particular problem. But we do need this to be greater than 0, and we need this to be greater than 0. And we have the nice relationship here. So K1 has to be greater than minus 6, K2 has to be greater than minus 5. And if we are stable. So we can now start to look at, so this will give us our stability. I want to look at control effort first. We wanted to see, so CT slash dot, I'm going to say K1. Actually, we can look at, before we do that, we might even want to, let's look at the poles first. So for example, let's do K1 is 10, K2 is 10. Let's look at what this looks like. So I'm going to expand that a little bit. So we've got a pretty good response. So why don't we play around with that? Let's just look. So let's go, I'm going to plot. And I'm going to do CT test. CT test equals CT slash dot. K1 goes to 10. K2 goes to 10. I'm going to just hide that output. I'm going to do CT test. Then I'm going to do YT test. So it's YT. And then ET test. ET. So good. So let's go ahead and let's plot now. Plot CT test from time from 0 to 10, comma plot range all. So, oof, too big. So, because we need it to never exceed a magnitude of 100, so let's do 3. Let's do 3. So let's do here. Test it out. We can go a little bit further. Let's do 4. 4. Let's see what we got. Too much. Let's do 3. 2. Ooh. Let's do 2, 2. 3, 3. Let's try this. And so now, actually, let's look at how does our y-test look like with those same values. So let's look at our y-test. Looks pretty good, right? So we had that steady state. So what are we looking for here? A rise time of less than 100 milliseconds. So that would be 0.1 second. Steady state error. Let's look at the steady state error. Lot ETT test. So we've got some values of our controller, and now we can start to look at our systems here. And there's a couple of little typos that I can kind of see here. So we need to have a rise time. It's actually not less than 100 milliseconds. We need a rise time less than 0.8 seconds. So let's correct that, 0.8. We also need a time to peak that's less than 3 seconds. So, and we need to be able to calculate those explicitly, and then this is basically gone here. So let's go ahead, let's go back. Where's our Mathematica? So you got our controllers, and also the steady state error must be less than 10 for all times. Actually, excuse me, let's make this less than 11. So we'll go ahead, less than 11 for all times. So we're okay there. So let's go ahead and look at our, so let's make sure for our controller, we're good. So we're less than 100. For our error, we're good. Fantastic. So now we just need our YT test. So we're going to go ahead and say my YT test / .t goes to large values. Let's look at this numerically. So my steady state is equal to 3.75. So now we can say, well, for my, actually peak might be easiest. Let's do peak time first. So we find root where the derivative YT test with respect to t, set this equal to 0 and solve for t goes around, let's see, 0.6, 0.5. Ooh, about 0.4. So actually, this might not be a maximum. So let's go ahead, the time to peak, let's change our system just a little bit. We can look. So for example, let's do this. 1, 1. We're just looking at some values here. All right, so we're still okay here. Let's look at our YT test. Now we got a nice little bit better of a bump. And so peak, let me get this value here. Our YT test now is actually 1.677. Let's look at our error. Nope, we're good here. So let's go ahead, let's set this. Let's find our time to peak. So now let's look over here. Where is our time to peak? Oops, let's go down. Oops, maybe I need to go up here. So about 0.2, 0.3. Let's start at 0.2. Excellent. So this is our time to peak. Peak time. So we're fine there because we need to be less than, what was it? Our time to peak had to be less than 3 seconds. And then let's do similar for our rise time. let's see. Let's go ahead and calculate. So we'll just start at really low values, and we won't go above 0.16. So I'm going to say, oops. Let's go through here. Find root, YT test, set it equal to 0.1 times steady state. Let's look at 0.01. So we can double check that value. /.t goes to here. Yep. And then we can copy and paste this here. 0.9, then 0.1. Excellent. So our rise time, and let's double check this value. So it should be 90% of 1.677. Looks pretty good, right? So our rise time will be equal to this minus this. So peak time, we've hit it. Rise time, we're definitely okay. So we're less than 0.8. And then we could also do steady state, or actually settling time, excuse me, while we're at it. So why not? So let's go. Let's say we need to be, when's the last time we get 0.9 of our steady state? When's the last time we get 1.01? Well, looking at our time response here, over 1.677. So let's start looking at like 8 for over. So like 8 seconds. Not changing, good. So let's go ahead, let's say YT test /.t goes to, so yep, that looks about to be, if we add on to the, if I do 1.01 times steady state, good. If we go to 20, it's not changing, excellent. What about here? Let's start again around 8. Ooh, it doesn't like, how about 4, 2, about 1, about 0.1. Yeah, so the last time is our rise time. So our settling time is 6.7, settling time is 6.7. So even though it doesn't ask for that, there we go. We're good. See you in the next problem. Thanks. Bye.